Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Look up on a clear night, far from the city lights. Above you stretches an endless dark ocean sprinkled with stars. The longer you gaze, the more stars appear, as if the universe is revealing a secret tapestry. Each star is a sun, distant and powerful. Our own sun is just one among hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is one among trillions. In fact, astronomers estimate there may be 2 trillion galaxies in the observable universe. Try to imagine that. 2 trillion island universes, each brimming with stars beyond counting. If you could snap your fingers and count 1 galaxy per second, you'd be counting for over 65,000 years just to list them all. Within those galaxies are countless worlds. Some scientists say as many as 6 billion Earth-like planets may orbit stars in our Milky Way alone, and perhaps 12 quintillion across the cosmos. 12 quintillion Earths, 12 quintillion possibilities. The scale of space truly defies comprehension. It's a void, a vastness, but also a canvas of nearly infinite possibilities. Floating on a tiny rock called Earth, we humans have always felt small under this sky. Tiny, yet special, because we can ponder it. We can ask, what is all this? What is the nature of space, of reality? How amazing that the universe is comprehensible enough that we can study it, yet mysterious enough to inspire wonder. As the famous astronomer Carl Sagan once said, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. We are made of atoms forged in long, dead stars, now come alive to gaze back at the sky. Through us, the universe questions its own existence. And one of the most profound questions we can ask is, are we even real? Could all this enormity, this grand cosmos, be an elaborate illusion or construction? Could we, our lives, our planet, our universe, be part of a grand cosmic simulation? That question sounds like science fiction, yet it has leapt from the pages of novels and movie scripts into serious scientific and philosophical debate. What if our reality is not the base reality? What if it's a program, running on some unfathomably complex computer, created by entities beyond our realm of existence? It's an idea that can feel both thrilling and unsettling, the simulation hypothesis. In essence, this hypothesis suggests that what we perceive as the physical universe, including space and time, might be an artificial simulation, like a high-resolution virtual reality designed by an advanced intelligence. In other words, maybe we are living in someone else's computer program. Pause for a moment and really consider that. The ground beneath your feet, the air you're breathing, the light from those distant stars, could all of it be code? If it were true, if everything we know is part of a simulation, how would we know? Would it even matter to us inside it? And who, or what, might be the programmer of the cosmos? These questions take us to the edge of what science can speculate and what philosophy can ponder. They force us to confront the nature of reality from a perspective that is both deeply cosmic and intensely personal. Tonight, we'll embark on a journey through this maze of ideas. We'll wander the vastness of space, marveling at its wonders, and we'll delve into the simulation hypothesis, examining why some prominent thinkers believe it might be true and why others remain skeptical. We'll touch on ancient philosophical puzzles and cutting-edge scientific experiments. We'll meet the scientists and philosophers wrestling with these questions, from those studying the quantum underpinnings of reality, to technologists pushing the boundaries of virtual reality, to philosophers questioning whether real and simulated are even meaningful distinctions. Along the way, we'll peer into the very code of the universe and see if there are hints that reality has a designer, and we'll imagine what it would mean for our lives, our purpose, our future, if we are indeed characters inside a grand cosmic simulation. This idea, questioning the reality of reality, is not entirely new. Long before computers and simulations, humans sensed that the world might not be exactly as it appears. Over 2,000 years ago, the Greek philosopher Plato proposed a famous allegory. Imagine people who have lived chained in a dark cave all their lives, Plato said, facing a blank wall. All they ever see are shadows cast on that wall, shadows of objects behind them, objects lit by a fire. Those shadows are their entire reality. They give them names. They think they're real things, but they're just projections, mere silhouettes of something truer. One day, a prisoner is freed and stumbles outside into the dazzling sunlight. For the first time, he sees the full, rich world beyond the cave and realizes the shadows were just a pale imitation of reality. Plato used this allegory of the cave to discuss knowledge and enlightenment, but it resonates eerily with the simulation idea. If we are like those cave prisoners, then our day-to-day world might be the shadow play, while the true reality exists outside our current perception. Could it be that we are living in a cave of sorts, seeing shadows and mistaking them for the whole of existence? Across cultures, similar notions appear. In ancient Chinese philosophy, Zhuangzhou wrote of a vivid dream in which he was a butterfly fluttering about. In the dream, he was happy, unaware of any other life. When he awoke, he found himself lying in bed as a man, but then he wondered, was he a man who had dreamed he was a butterfly, or a butterfly now dreaming he was a man? This butterfly dream story captures a deep puzzle. How can we know if our experience right now is real, or some kind of dream or illusion? Likewise, in Hindu philosophy, the concept of Maya describes the world as an illusion, a sort of cosmic play. And the French philosopher René Descartes, in the 17th century, famously imagined an evil demon that could be tricking him with an illusory world, an early pondering of a virtual reality created to deceive the senses. Descartes realized the only thing he couldn't doubt was his own mind's existence, which is not so far from the simulation question. If everything were simulated, the one thing we might be sure is real is our own consciousness experiencing it. We humans have a long history of questioning reality, but the simulation hypothesis, as we discuss it today, took these age-old questions and reframed them in the context of modern technology and cosmology. It's as if the ancient philosophical doubts met the era of computers and video games and found a new form. A key moment in popular culture was the release of The Matrix in 1999, a film that riveted audiences with its depiction of humans unknowingly trapped in a perfectly simulated world. People plugged into a virtual reality, living in a shared illusion while their bodies lay elsewhere, asleep. The Matrix wasn't the first story of its kind, but it presented the idea so powerfully that it became a cultural touchstone for this concept. Suddenly, the question, what if we're in a simulation, moved from esoteric philosophy to everyday conversations. After watching Neo choose between the red pill and blue pill, a whole generation had a reference point for discussing the nature of reality. Just a few years after that film, in 2003, a philosopher named Nick Bostrom at Oxford University gave the simulation idea a rigorous academic form. Bostrom wrote a paper with a title that cuts straight to the core: Are you living in a computer simulation? In it, he proposed a sort of logical argument, a trilemma. It goes something like this. 1. Almost all civilizations at our stage of technological development go extinct before they ever become technologically posthuman. In other words, maybe it's incredibly rare to survive long enough to create the kind of computing power needed for world-sized simulations. 2. If a civilization does reach that advanced stage, perhaps almost none of them would be interested in running simulations of minds like their ancestors. Maybe it's simply not done. whether for ethical reasons or lack of interest. 3. If the first two propositions are wrong, then the number of simulated conscious beings would far, far exceed the number of original beings. And if that's the case, the odds are that we ourselves are among the simulated minds, not the original biological ones. Bostrom argued that at least one of those three must be true. Either we're doomed to never reach that advanced stage, or we'll reach it, but never simulate worlds with conscious beings, or we're almost certainly in a simulation right now. Importantly, if you think there's any significant chance that advanced civilizations would run such simulations, then you have to admit the possibility that we might be in one. To put it another way, unless we go extinct or never bother to use our future computers this way, it's quite likely that reality as we know it is a digital illusion. That's the unsettling logic Bostrom presented. He even concluded, somewhat playfully yet provocatively, that the belief that there is a significant chance that we will one day become posthumans who run ancestor simulations is false, unless we are currently living in a simulation. In simple terms, we can't have it both ways. We can't both expect our descendants to create loads of simulated worlds and also assume we're in the one real world. If creating simulated universes becomes possible and common, then statistically, our own reality is probably one of the many simulations rather than the one original. This argument hit the scholarly world like a jolt. It was a serious professor, not a Hollywood director, suggesting this mind-bending scenario in earnest. And it came at a time when computing power was growing exponentially, and our own simulations, think computer games, virtual reality experiments, AI programs, were becoming more impressive every year. Bostrom's paper gave a sort of credibility to an idea that, until then, was mostly science fiction. It moved the conversation into journals and conferences. People began to debate, not just, could this be true, but what evidence would there be, and how would this change things? It didn't stay in academia. The idea spilled out into tech companies, into late-night dorm room discussions, into Reddit forums and YouTube channels. Even major public figures started taking it seriously. Perhaps the most famous among them is entrepreneur Elon Musk, known for his ventures in electric cars and space travel. Musk has repeatedly talked about the simulation hypothesis. In 2016, speaking at a conference, he put it in his characteristically blunt terms. There's a 1,000,000,000 chance we're living in base reality, meaning he thinks the odds that our reality is the original reality are almost zero. In other words, Elon Musk believes it's extremely likely that we are living in some kind of computer simulation. That statement grabbed headlines around the world. Here was one of the most high-profile innovators on the planet, casually asserting that everything we experience might be artificial. Musk's rationale was simple. Look at the trajectory of video games. In the 1970s, we had Pong, 2 rectangles and a dot. Today, we have hyper-realistic 3D simulations with millions of players in richly rendered worlds and virtual reality technology that can trick our senses for a time. Given another few decades or centuries, the argument goes, it's inevitable that our technology will produce simulations indistinguishable from reality. If we have that potential, then perhaps some other civilization in the universe already achieved it. And if even one civilization did, the number of simulated universes could be astronomically large. So from Musk's perspective, the math makes it hard to believe we are the one lucky draw that is actually real. He's not alone. Astrophysicist Neil deGrasse Tyson, a science communicator who hosts TV shows and podcasts, has said he thinks there's a very high chance the universe is a simulation. At a debate in 2016, Tyson suggested the likelihood might be better than 50-50 that we live in a simulation. Philosophers like David Chalmers and physicists like Max Tegmark have also entertained the idea in public discussions. Suddenly, the simulation hypothesis has moved from a fringe idea to a topic discussed by scientists at prestigious forums. In fact, the American Museum of Natural History held an entire panel debate on it, with experts from different fields. One journalist described that debate, noting that philosophers, physicists, technologists, and, yes, comedians are all grappling with the idea. It has, in a sense, become mainstream speculative thought. But let's step back a moment. Is there any evidence for this idea, or is it all circumstantial and philosophical? Why would serious people even consider that we might detect the telltale signs of a simulation? To explore that, we need to delve into the nature of physical reality itself, into space, time, and the quantum realm, and see if our universe behaves the way we'd expect a base reality to behave, or if it has quirks more suggestive of a programmed environment. First, consider the nature of space. We usually think of space as simply emptiness. You might picture the void between stars as a silent, cold nothingness. But in physics, space is not truly empty. It has properties. It can bend, ripple, and even boil, with tiny particles popping in and out of existence. According to Einstein's theory of general relativity, space is like a fabric that can stretch and curve. Massive objects like stars and black holes warp this fabric, which is what we feel as gravity. Space, in this view, is dynamic. It's not just an empty stage where things happen, it's part of the actors. When we observed gravitational waves from colliding black holes for the first time in 2015, it was literally space itself trembling, like a pond rippling when a stone is dropped. This is a far cry from the simple nothingness one might assume space to be. Now, zoom down to the tiniest scales, and space gets even weirder. In quantum mechanics, even what we call a vacuum seethes with activity. Particles and antiparticles can spontaneously appear in pairs, exist for a fleeting moment, and annihilate each other. A phenomenon allowed by the quantum rules, as long as it's brief. This isn't science fiction. It's been experimentally observed. If you think about it, this is almost like the universe has a constant background computation running, even when nothing is there. It's as if the simulation never truly idles. There's always some processing happening in the vacuum of space, a constant quantum hum. What about the size of space? The observable universe, the part of the cosmos we can in principle see, extends about 46 billion light-years in every direction from us. We often say 13.8 billion years old, but due to expansion, the radius is larger in light-years, and that's just what's observable. Space could be much larger, potentially infinite. If a simulation were to recreate such a vast space in full detail everywhere, the amount of information would be mind-boggling. Could any computer, even one built by gods or advanced aliens, simulate 2 trillion galaxies worth of stars, planets, and particles? It seems intractable. But if we were inside a simulation, there might be ways to cheat and not simulate everything at once. Think of how video games work. When you're playing a game, the computer or console isn't rendering the entire game world at high resolution all the time. It's only rendering what the player is currently seeing or experiencing. Turn away from a scene, and the game might stop calculating it until you turn back. Some have suggested that a universe simulation might do something similar, only calculate details as needed. This ties into one interpretation of quantum physics that's frequently mentioned in the context of simulations: the idea that observation seems to play a role in how quantum events resolve. There's a famous experiment, the double slit experiment, where particles are fired at a screen with 2 narrow slits. If you don't observe which slit a particle goes through, the particle acts like a wave of possibilities, going through both slits and creating an interference pattern on a detector screen, as if it interfered with itself. But if you set up a detector to watch the slits, the interference pattern disappears. The particle behaves like a single, well-defined object that went through one slit or the other. Simplifying a lot, the outcome changes depending on whether it's observed. To many, this suggests that reality decides on an outcome only when it has to. when an observation is made. This is a cornerstone of quantum mechanics, often summed up as the observer effect. Now, some physicists will caution that it's not that consciousness causes the change per se, just the interaction with a measuring device. But the philosophical interpretation lingers. Perhaps things aren't determinate until they need to be. If you were designing a simulation, that's actually a smart way to save resources. Don't calculate something until someone tries to look at it. In a way, the universe already behaves like that at the quantum level. It's as if there's a level of reality that's in potential form, a haze of probability, and it becomes concrete only upon interaction. Could that be the sign of a rendering engine at work? As Tyson and his comedian colleague Chuck Nice quipped on Star Talk, maybe that's why we have the speed of light limit in our universe. Perhaps the simulation doesn't allow anything to travel faster than light, because then you could get to another star or galaxy faster than the program could load the details. In their playful exchange, Chuck Nice suggested, maybe that's why we can't travel faster than the speed of light, because if we could, we'd be able to get to another galaxy before they can program it. And Tyson added with a laugh, so the programmer put in that limit. It's a joke, but it perfectly illustrates how a computational constraint could manifest as a law of physics. Our cosmic speed limit might be akin to the draw, distance in a video game, preventing us from moving too fast for the simulation to keep up. Let's think about other hints. Some scientists have looked for signatures of discretization in space, essentially evidence that space is not continuous, but made of tiny pixels or chunks, like a digital grid. If the world is simulated, it might be running on a lattice or grid at the smallest scale. In our current physics, we have the concept of the Planck length, which is far smaller than anything we can directly measure. It's often thought of as a scale at which classical ideas of space break down and quantum gravity might take over. If space were truly pixelated, the Planck length might be the size of the pixels. A few researchers have proposed experiments to detect this. Dr. Zohre Davoudi, a physicist at the University of Maryland, has discussed how, if space-time is discrete, there could be slight changes in how high-energy particles travel across cosmological distances. For instance, we might detect a tiny preferred direction or an upper limit in the energy of cosmic rays because of the underlying grid. Imagine if you tried to draw a perfectly straight, extremely long line on a pixelated screen. At some point, the discreteness might show anomalies. Davoudi specifically noted that if space-time is on a lattice for the simulation's sake, extremely energetic particles might not behave exactly as expected in a smooth continuum, possibly revealing a break in a symmetry-like rotation. So far, no such anisotropy in cosmic rays has been observed. If one were, it would be intriguing, though not absolute proof of a simulation. But the fact that physicists are even contemplating such tests shows how seriously the idea is being taken. Another striking piece of maybe evidence came from James Gates, a theoretical physicist known for his work in supersymmetry. Gates found something unexpected in the equations he was studying. Deep in the mathematical framework of certain supersymmetric models, he discovered equations that are identical to those used in computer error correcting codes. Error correcting codes are algorithms programmers use to ensure data isn't corrupted. Basically, they help systems self-correct mistakes. They are, as Gates put it, what make browsers work, allowing digital information to transmit reliably. So, it was quite startling to find them knitted into the fundamental equations describing how particles and forces might work. Gates said, "I no longer can say that people like Max Tegmark are crazy." Upon realizing this, implying that seeing something so digital, looking in the bedrock of physical law gave him pause. He mused that finding such code in nature's equations, if nature weren't a simulation, would be an extremely unlikely coincidence. Does that mean the universe is a computer program? Not necessarily. It could be that our mathematics just happens to take that form, or perhaps there's a deeper reason for those codes that has nothing to do with actual computing. But it's tantalizing details like this that make scientists raise an eyebrow. It's as if you were walking through a forest and found a computer chip lying on the ground. You'd wonder, is there an intelligence at play here, or is it just an odd-shaped rock that happens to look like a chip? Cosmologist Max Tegmark, whom Gates referenced, has pushed an even broader idea, that the universe fundamentally is mathematical. Tegmark often points out that the more we study nature, whether it's the motion of planets or the behavior of subatomic particles, we find that mathematics describes it with uncanny precision. The laws of physics can be written in equations. They have symmetry and structure, much like a code. Tegmark's perspective is that perhaps the universe isn't just described by math, it is math in a very real sense. If one were a character in a video game, he notes, at some point you might notice the strict mathematical rules of your world and suspect there's an underlying code. Our scientists, by uncovering equations, might just be reading bits of the cosmic source code. This doesn't prove a programmer in the usual sense. Tegmark is careful to frame it as the universe being a mathematical structure on its own, but it certainly rhymes with the simulation narrative. After all, what is code, if not mathematics, implemented in a machine? So from the quantum behavior suggesting on-demand rendering, to potential spatial pixels at Planck scales, to literal error, correcting codes popping up in theoretical physics, the universe has some hints that tickle the mind. None of these are smoking guns. For every intriguing clue, skeptics can offer alternative explanations, but they add up to a picture of a universe that is surprisingly information-like. The physicist John Wheeler once coined the phrase "it from bit," meaning that at a fundamental level, everything may arise from binary choices, from information bits. More and more, our best theories of physics speak in terms of information. Black holes, for example, are often described by how they store information on their event horizons. Quantum entanglement is being investigated as the possible pixel glue of space-time itself in some modern theories. Scientists are exploring the idea that space-time geometry might emerge from patterns of entanglement, essentially from information networks. It's almost as if the universe behaves like a giant information processor. And if so, one can't help but ask, who or what is processing that information? Is it just the universe being the universe? Or is it a computer built by something beyond it? Now, let's take a step further out and look at a completely different line of thinking, the Fermi paradox and the eerie silence of the cosmos. In our opening, we talked about the vastness of space and the countless planets that likely exist. Given those numbers, many scientists believe that life, and eventually intelligent life, should have arisen in many places across the cosmos. Even if a fraction of those 12 quintillion Earth-like planets developed life, and a fraction of those developed intelligent civilizations, there ought to be many alien civilizations out there, some perhaps far older and more advanced than us. This reasoning is encapsulated in the Drake equation, which is a probabilistic formula to estimate the number of communicative civilizations in our galaxy. Depending on what numbers you plug in, you might predict anything from 0 to thousands of civilizations. But many reasonable estimates suggest the galaxy should be home to several at least, and the universe at large, many more. So physicist Enrico Fermi famously asked, "Where is everybody? If life is common, why haven't we seen any evidence? No confirmed signals, no spacecraft, no alien visitations that withstand scientific scrutiny. The skies are quiet and have been for as long as we've been listening." This puzzlement is what we call the Fermi paradox. Over the years, people have suggested numerous possible solutions. Maybe life is rare, or intelligent life destroys itself quickly, or maybe alien civilizations are out there but choose to hide or observe us from afar. One particularly mind-bending proposal is directly relevant to our topic. Perhaps we don't see aliens because the universe has been designed to appear empty to us. This is sometimes called the Planetarium hypothesis. Imagine we are inside a giant virtual planetarium or terrarium, crafted to give us an illusion that we are alone. In 2001, science fiction author Stephen Baxter wrote an essay suggesting exactly this: that maybe advanced extraterrestrials, perhaps ones who reached a Type 3 civilization on the Kardashev scale, have created a simulation around us so that we perceive a vast, empty universe. They keep us in the cosmic equivalent of a snow globe. We look out and see stars and galaxies, but maybe the details beyond a certain point are all a projected illusion. Baxter wrote that our universe could be a form of virtual reality planetarium designed to give us the illusion that the universe is empty. In this scenario, the reason for the simulation is key. It might be to quarantine us or protect us. Perhaps they worry that if we knew about them, or if we encountered them, it would disrupt our natural development, or cause us to panic. Or maybe it's to protect themselves, ensuring we can't locate them. It's a wild idea, but it does answer Fermi's question in a creative way. We haven't seen aliens because our reality is constructed so that we won't. Whenever we point our telescopes out and listen for signals, the simulation dutifully returns a result of grand silence because that's its programming. If true, it implies our simulators are not necessarily our descendants, but could be alien beings in a higher level reality. They might be running a simulation of the universe and intentionally omitting themselves. It's like we're NPCs in a video game who aren't allowed to meet the game masters. Of course, if that's the case, what happens if one day we humans start reaching out into space in earnest? Baxter mused that maybe the simulation has built in limits to stop us. For example, the laws of physics that limit space travel could be intentional. The enormous cosmic distances and the finite speed of light act as barriers to keep us from ever leaving our sandbox region of the simulation. If somehow we got close to escaping, say we built ships that approach light speed, perhaps the simulators would intervene with some new obstacle. It's a bit like the Truman Show, where the main character tries to sail away from the island and literally bumps into the sky, which is a painted dome. Is our sky, our space, a painted dome in some sense? Hard to believe, and currently impossible to know. But it certainly fires the imagination. Now, before we get carried away, it's important to note that while some researchers find such ideas intriguing, they also acknowledge limitations and criticisms. For instance, can a simulation even be that large and perfect? One challenge is what we call computational complexity. If you were to simulate an entire universe down to the level of atoms or quarks, the amount of computing power seems unfathomable. We struggle to simulate even a tiny chunk of the physical world with our best supercomputers. Simulating the quantum behavior of a few dozen particles can tax our largest machines. In fact, researchers using quantum Monte Carlo simulations find that the complexity grows exponentially with the number of particles. They've pointed out that to simulate just a small piece of reality at full quantum detail might be effectively impossible for any practical computer, even one the size of a planet or a star. So skeptics argue, how could a simulator handle 10 bar 80 particles, each doing their quantum dance? Well, proponents of the simulation idea respond that a simulator could use shortcuts. We already touched on one. Only simulate what's needed. Perhaps the simulating computer doesn't bother to calculate the interior of distant stars or the exact behavior of every galaxy unless it becomes relevant to the story. Perhaps it focuses on Earth and its vicinity, and everything else is painted in broad strokes, with detail filling in only when we look closely. Some have even speculated that things like quantum indeterminacy or chaos theory could be features that prevent us from ever predicting and thus compressing the universe's behavior. If the simulators are clever, they might not need infinite power, just very sophisticated algorithms that always stay a step ahead of the players. Another counterargument is Occam's razor. This is the idea that, all else being equal, the simplest explanation that fits the data is preferred. The simulation hypothesis is, to put it mildly, not the simplest explanation. It posits an entire additional layer of reality, with beings and technologies far beyond our own, all to explain a universe that we could otherwise just take as is. Physicist David Kipping performed a Bayesian analysis and initially found about a 50% odds for us being in a simulation, given no prior information. And he noted that if humanity ever creates simulations of conscious beings, those odds would dramatically tip toward the simulation scenario. But Kipping himself has said that because the simulation idea is so elaborate, Occam's razor might count against it. Without evidence, why assume a complicated multi-layer reality when a single-layer reality works fine? He and others have likened it to a philosophical speculation that may not be testable, and if it's not testable, can it be considered scientific? After all, any evidence we find could be just features of the universe, not proof of external programming. The ultimate problem is falsifiability. We can't currently devise an experiment that would definitively tell us, yes, this is a simulation, or no, it's not. If the simulation is perfect, any result is just part of the simulation. As philosopher David Chalmers put it, there's certainly not going to be conclusive experimental proof that we're not in a simulation. Any evidence we could ever get would be simulated. In other words, a clever simulator could always tweak things to keep us guessing. So some argue, what's the point of even debating it if we can't prove or disprove it? Perhaps, they say, we should just proceed as though the universe is real. Lisa Randall, a prominent physicist, has expressed that she finds the simulation hypothesis pretty implausible and not very useful. We might as well keep doing science and not worry about being in a simulation. She remarked, "We don't know the answer, and we just keep doing science until it fails." If at some point our scientific understanding truly hits a wall that can only be explained by, "we're in a sim," then maybe we'll reconsider. But until then, the hypothesis is more of a fun thought experiment than a practical guide. Randall also noted that thinking about such scenarios can still be valuable if it motivates us to ask interesting questions about physics we can test. In a sense, even if we don't buy the simulation theory wholesale, exploring it might spark new ideas or new ways to look at the cosmos, and that is certainly worthwhile. Now, let's imagine for a moment, what if we did discover evidence we're in a simulation? Or suppose one day an anomaly happens that simply can't be brushed aside. Maybe a message appears in the sky that can't possibly be natural, or we find an actual glitch in physics that is so specific it points to design. How would we react? Would it change how we live our lives? There are many science fiction scenarios about this. One could imagine society reacting with denial, or with a religious fervor, or maybe with panic, or conversely with relief. That explains everything. It's hard to know. Some thinkers have said it shouldn't change much on a day-to-day level. If you find out the universe is a simulation, the tree in your backyard is still a tree. The love you have for your family is still real to you. The taste of your favorite food is the same. You still have to go to work, avoid stepping in front of buses and all that. In fact, in a perfectly run simulation, you can't actually do anything outside the rules of the simulation, so you'd have to continue living by its laws. But psychologically, it could be a heavy realization. Would people feel less guilty about doing wrong, thinking, none of this is real, so what does it matter? Or would they feel more purpose, like, we're part of a planned creation, we better make our creators proud? Different individuals might react differently. Interestingly, the simulation hypothesis has a way of merging with traditional ideas of spirituality and religion. If there are creators outside our reality who made our world, how is that so different from concepts of God or gods? Some have pointed out that the simulation argument is like a technologically updated creation story. Instead of a supernatural deity, you have a super intelligent programmer. Instead of mystic heaven, you have another universe that hosts the computer. It reframes phenomena like an afterlife. As Dr. James Gates noted in that panel, if we are in a simulation, reincarnation might be literally possible. Our lives could be restarted or the program run again, effectively bringing everyone back to life. If you've ever played a video game, you know that dead characters can often respawn, or a saved game can be loaded to replay a scenario. In a simulation, maybe death isn't permanent, The data of your mind could be saved or copied. The simulation could also allow for things that look like miracles. Perhaps the simulators can intervene or tweak things now and then, which might appear to us as divine acts or anomalies. It's a whimsical parallel, but it does start to blur the line between science fiction and theology. In fact, Gates said that the simulation idea starts to break down a funny barrier between what people often think is the conflict between science and faith. Because here we have a scenario with creators, possibly an intention or purpose, and potentially even a form of life after death. Yet it's framed in a logically and technologically grounded way, rather than a mystical one. It's almost like a bridge between two worldviews. Of course, not everyone would agree with venerating simulator beings as gods. Philosopher Chalmers quipped that even if we were in a simulation controlled by higher beings, he'd refuse to worship the simulators. After all, they might be just scientists or gamers, not morally superior divinities. And if they allowed suffering in the simulation, one might question their ethics just as we question why a benevolent God would allow evil. Are we just an experiment? Entertainment? Education? Who knows what their motive would be? There's even a theory that maybe it's us, our future descendants, running ancestor simulations to study their own history, which raises all sorts of paradoxes and moral questions about creating conscious beings for study. Bostrom himself pondered on whether it would be ethical to run simulations of suffering. Let's entertain a positive angle. If we are in a simulation, maybe the simulators are benevolent. Perhaps we're a kind of long-term art project, being carefully tended. If at some point we're in danger, maybe they'd subtly steer things to save the project. Some people have humorously suggested that the lack of catastrophic asteroid impacts in recent times, or the fortuitous timing of certain events in humanity's past, could indicate someone wants us to reach a certain stage. That's highly speculative and arguably just human-centric storytelling. But it's true that the simulation idea can either make you feel extremely small or strangely important. Another fascinating speculation: what if we ourselves create simulations within this universe? If we build our own simulated realities, populated by AI beings who think they're alive, then we'd have a nested simulation. Perhaps that's already happened. Maybe the simulators who built our world are themselves simulated by a higher level, and so on. This could lead to a chain of simulations within simulations. Tegmark pointed out a philosophical issue with Bostrom's argument. What stops an infinite regress of simulated worlds? If simulations become common, there could be many layers. But could it be simulations all the way down? At some point, there might need to be a base reality where the first simulation runs. If we're deep in a stack of simulations, our chances of reaching or understanding the true base reality are extremely slim. It would be like a character in a video game becoming aware of the game and then trying to figure out the world of the game developers by only exploring inside the game. They might get some hints, but can't break out of their level. Some tech visionaries have even talked about trying to break out of the simulation. There were reports that certain billionaires in Silicon Valley were funding research to find a way to detect or escape the simulation. It sounds like the plot of a movie. The rich and brilliant trying to crack open the sky of the Truman Show. While those specific stories might be exaggerated, it's true that the simulation hypothesis has captivated some of the most future-oriented minds. If you truly believed we're in a simulation, one radical idea would be to attempt to communicate with the creators. Maybe not by building a physical Tower of Babel, but perhaps by sending a clever message or creating a scenario within the simulation that stands out. Some have facetiously suggested that we should perform bold, unpredictable actions so as to get the simulator's attention. Max Tegmark, at the end of that debate, half-jokingly advised, "If you're not sure whether you're actually simulated or not, my advice to you is to go out there and live really interesting lives and do unexpected things so the simulators don't get bored and shut you down." That might be the best advice regardless of simulation status. Live an interesting, meaningful life, just in case someone is watching from above, and for your own sake if no one is. Now, we've journeyed through a lot, from the starry expanse of space to the subatomic quirks of quantum physics, from ancient philosophy to cutting-edge computational theory, from the loneliness of the cosmos to the possibility that we're not alone at all, but rather surrounded by an invisible infrastructure of a simulation. Through it all, one thing is clear: the line between reality and illusion is delicate. Whether or not we live in a simulation, pondering it forces us to appreciate reality's richness. If our universe is a simulation, it's a masterpiece of one. Think about it. The simulators would have created every coral reef, every nebula, every laugh, every tear, the taste of chocolate, the laws of gravity, the music of Mozart, the equations of Newton, the light of 1 billion trillion stars. And they gave us the tools, like science, to start to figure it out. That's quite something. And if this is not a simulation, if this is the one true reality, then it's even more incredible. It means from empty darkness and mindless matter, the universe evolved to a state where it can dance and think and wonder through us. We, tiny specks on a pale blue dot, can question the very fabric of existence. In the end, the simulation hypothesis is a mirror. Look into it, and it reflects our deepest inquiries. It asks how far our intelligence can go, how we distinguish truth, how we find meaning. It has us grapple with what-ifs that challenge our perception of time, space, and ourselves. Are we a cosmic accident, alone in an unconscious universe? Or are we characters in a cosmic play with hidden audience and playwright? Perhaps we'll never know for sure. Perhaps one morning, like Zhuangzi, we'll wake up and realize this was all a dream. Or maybe we'll venture out into space, among the real stars or the simulated ones, and gradually peel back the layers of reality. Until then, the best we can do is live fully and curiously. Simulated or not, this life is the one we have. If it's a simulation, maybe we honor it by being the most interesting simulation we can be. If it's base reality, we cherish the fact that we're part of something truly fundamental. In both cases, our experiences, our joys and sorrows, our aspirations, they matter to us and to those around us. As far as we're concerned, they are real. The philosopher Chalmers might remind us, even if all is a simulation, the simulation is our reality, so it's real to us. So when you next step outside on a crisp night and look up, consider the stars again. Each one could be a distant sun in a vast, real galaxy, or a pixel lit up on the canvas of a sky created for our benefit. Either way, let that sight fill you with wonder. The universe, be it natural or programmed, is majestic and mysterious. We find ourselves alive in the midst of it, able to ask grand questions. That is a privilege beyond measure. In a way, through our eyes, the universe gets to witness something too. A species growing from curiosity, reaching out for truth, striving to understand the infinite. Perhaps that's the point of it all, to wonder. Perhaps the ultimate cosmic experiment is to see if intelligent life can figure out its own reality, or at least learn to live harmoniously within it. We may not have the final answers, but we will keep searching, observing, hypothesizing. We will keep exploring space, both outer and inner, physical and virtual. And as we do, we carry in our minds the profound possibility that reality might be far more layered than it seems. It's a possibility that humbles us, but also elevates our imagination. Real or simulated, the stars still shine down, the night sky still calls to us. The mystery remains as deep and dark as space itself. And in that mystery lies beauty, because a universe without secrets, simulated or not, would be far less interesting. So let's embrace the mystery. Let's cherish the awe we feel when confronted with the cosmos. If we are in a simulation, then let's be the best characters we can be. And if we're not, let's be the best beings this universe can produce. In the end, Perhaps it doesn't matter whether our reality is base level or virtual. What matters is what we do with the reality we have. As the great adventure of knowledge and existence continues, we remain, as always, explorers. Explorers of space, explorers of ideas. We stand on the shore of the cosmic ocean, with the waves of the unknown gently lapping at our feet. Above us, the sky, real sky or manufactured dome, is full of stars. We feel small, yet connected to something vast. We feel the urge to reach out, to understand. And so we journey on, minds wide open, hearts alight with wonder. Who knows what we'll discover, what truths or illusions await? The nature of space and the mystery of the simulation hypothesis together form a story still unfolding. Stay curious, keep looking up, and remember, the universe is far more wondrous than any fiction ever conceived. Possibly because, in some way, it might be a fiction, crafted with care. Or perhaps because a simple truth underlies it all. Either way, it invites our curiosity, and that, in itself, is the grandest invitation we could ask for. Now that our main story is to a close, let's list some space facts. Imagine a place in the universe where a single spoonful of material weighs more than Mount Everest. Neutron stars, the ultra-dense remnants of massive stars, are so compressed that just 1 cubic inch of their matter would tip the scales at billions of tons. These stellar corpses are the densest objects known outside of black holes. Their magnetic fields are trillions of times stronger than Earth's, a city-sized ball of neutrons, spinning at hundreds of revolutions per second, crackling with radiation, isolated in the cold silence of space. A lighthouse of doom beaming through the dark. Step outside the airlock of the International Space Station, and something surprising happens. When astronauts return from their spacewalks, they often report a distinct smell clinging to their suits. Not the void itself, but the aftermath of exposure. The odor, burnt steak, welding fumes, a metallic tang. This is the scent of space, or at least how our senses interpret the byproducts of atomic oxygen interacting with spacecraft surfaces. It's the smell of the universe in motion, of particles colliding, of stars being born and dying. Venus, Earth's twisted twin, takes its time. If you were to stand on its blistering surface, where temperatures melt lead and clouds rain acid, you'd notice something even more bizarre than the heat. A single day on Venus, one full rotation on its axis, takes longer than an entire trip around the sun. That means its day is longer than its year. A planet where the sun rises in the west and sets in the east, crawling through a sky it barely crosses. Time stretches strangely on Venus, and so does our understanding of what makes a planet normal. Far beyond our galaxy, past swirling nebulae and clusters of galaxies, lies something extraordinary. Around a quasar, 12 billion light-years away, astronomers discovered a cloud of water vapor large enough to fill Earth's oceans. 140 trillion times. This ancient fog surrounds a supermassive black hole, glowing brightly with the energy of an entire galaxy. It's the largest and most distant water reservoir ever found. A cosmic oasis in the void, proof that even in the deep past, water flowed freely across the stars. The moon has always been our closest companion, our silent sentinel in the sky, but it's slowly drifting away. Every year, the moon moves about 1.5 inches farther from Earth. It may not sound like much, but over millions of years, it adds up. In the distant future, the moon will be too far to perfectly eclipse the sun. Total solar eclipses, those magical moments when day becomes night, will cease to exist. A celestial goodbye that spans eons, unnoticed in a single human lifetime, but profound in the timescale of the cosmos. Not all planets are tied to stars. Some wander alone. These are rogue planets, dark, cold worlds without a sun, flung into the abyss by gravitational chaos. Billions of them roam the galaxy like cosmic orphans, drifting endlessly through space. With no light to define their days and no warmth to shape their climates, they remain mysterious. Some may harbor subsurface oceans, heated from within. Others may be completely frozen, locked in a stasis that has lasted since the dawn of time. They are reminders that not every world belongs to a system. Some just float in solitude. The Sun, though just one star among billions, is a giant in our own neighborhood. It holds 99.86% of all the mass in the solar system. That means everything else, every planet, every moon, every comet and asteroid, is just debris in comparison. Even mighty Jupiter, the king of the planets, is barely a drop in the solar ocean. The Sun dominates not just through heat and light, but by sheer gravitational force. It commands the dance of planets, holds the icy edges of the Kuiper Belt in place, and bends the very fabric of space and time around it. Speaking of time, it's not as steady as it feels. In places of intense gravity, like near a black hole or even on a planet like Jupiter, time flows more slowly. This is not science fiction. It's the bizarre truth of Einstein's general relativity. Gravity warps space-time. The closer you are to a massive object, the slower time passes for you. Live your life orbiting a black hole, and you might experience minutes while years pass outside. Time is elastic in the universe, flexible, strange, and deeply tied to gravity. High above Earth, satellites orbit in perfect balance. But there's something else out there too: space junk. The modern sky is littered with remnants of human ambition, dead satellites, rocket parts, tiny fragments of old missions. Over 170 million pieces of debris now race around our planet, many traveling at speeds faster than a bullet. A single screw could punch through a spacecraft like shrapnel. It's a growing cloud of chaos, and one that we'll have to reckon with if we hope to keep exploring the stars. On the outskirts of the solar system, beyond Neptune, lies a vast and icy graveyard known as the Oort cloud. It's never been directly seen, but we know it's there. A shell of frozen objects encasing the solar system like a bubble. Some comets we see in the sky begin their journey here, drifting for millions of years before the sun's gravity gently tugs them inward. The Oort cloud may stretch halfway to the next star, holding the leftovers of solar system formation, ancient time capsules frozen in deep space. Jupiter is more than just the largest planet in our solar system. It's a shield, a protector, a cosmic vacuum cleaner. Its immense gravity pulls in comets and asteroids that might otherwise strike Earth. Without Jupiter, life here might never have had a chance. But this gas giant has secrets of its own. Beneath its swirling clouds lies a core of metallic hydrogen, a state of matter so exotic it can only exist under immense pressure. Lightning storms larger than Earth rage across its surface, and its iconic Great Red Spot is a hurricane that's been raging for centuries. Saturn's rings are perhaps the most visually stunning feature in the solar system, but they're young, maybe only 100 million years old, and they're vanishing. Slowly, inexorably, the rings are falling into Saturn, pulled down by gravity and magnetic forces. What once dazzled stargazers may one day disappear entirely. The rings are made mostly of ice, ranging in size from dust grains to bus-sized chunks. They're delicate, temporary, a reminder that even beauty on a planetary scale can be fleeting. And then there's Pluto. Once a planet, then demoted, yet still beloved. This distant world has a heart-shaped glacier on its surface and mountains made of water ice. But what's more fascinating is what lies beneath. Scientists believe Pluto may have a subsurface ocean, liquid water under layers of rock and ice. In the frozen reaches of the Kuiper Belt, warmth can still exist, not from sunlight, but from radioactive decay deep within. Even in the coldest places, the potential for life may remain. Let's drift even farther, to a galaxy not so different from our own, one of many. The observable universe contains more than 200 billion galaxies, and each of those galaxies contains hundreds of billions of stars. That means there are more stars in the universe than grains of sand on every beach on Earth. Yet despite this overwhelming abundance, the night sky feels quiet, peaceful, but it is anything but empty. It is alive with movement, with birth and death, with explosions and silence, with radiation and dust. Black holes, cosmic monsters that devour light itself, sit at the heart of many galaxies, including our own. The one at the center of the Milky Way, Sagittarius A, is 4 million times the mass of our Sun. Yet we can't see it directly. It lurks behind a veil of dust and gas, invisible and quiet, unless something dares come too close. Then, space-time tears. Matter stretches into glowing streams as it spirals inward, lost forever. Time itself slows to a crawl. And then, nothing. Beyond the event horizon, not even information escapes. And finally, we return to Earth, our pale blue dot. Floating in a sunbeam, Carl Sagan once said. All the wars, the triumphs, the laughter, and the sorrow, every human story that has ever existed, happened here. Earth is the only known planet to harbor life, but that may not last forever. Our star will die, our oceans will boil, but for now, we are here, thinking, dreaming, wondering, reaching out into the dark. There is a place where stars go to die, a graveyard not of bones, but of white-hot embers. White dwarfs are the final act of small to medium stars like our Sun. After billions of years of burning, they shed their outer layers and collapse inward, becoming a sphere of dense, glowing ash. These stellar corpses are no larger than Earth, but can weigh as much as the Sun. Over trillions of years, they cool and fade, becoming black dwarfs, cold, dark remnants that may be the final objects left in the universe, long after the last galaxies blink out. But not all stars fade quietly. The largest live fast and die violently. Supernovae are among the most powerful events in the universe, stellar explosions that outshine entire galaxies for brief moments. In that flash, elements like gold, silver, and uranium are forged. Every heavy atom in your body, in the Earth, in your phone, was born in a star's fiery death. We are, quite literally, made of star stuff. And those supernova remnants, they seed the galaxy with the building blocks of new worlds. In the vacuum of deep space, silence reigns. Not because there's nothing happening, but because sound cannot travel. Space is not just quiet, it is mute. There is no air to carry sound waves. Explosions, collisions, solar flares, all of it happens in absolute silence. If you were floating next to a star going supernova, you'd see light brighter than anything imaginable, and hear nothing. In space, even the loudest scream is swallowed by the void. Yet even the void is not truly empty. Between the stars, in the vast gulfs of interstellar space, is dust, gas, particles and radiation, invisible forces drifting in the darkness. Entire clouds of molecular gas stretch across light years, slowly collapsing under gravity to birth new stars. These are stellar nurseries, glowing, majestic regions like the Orion Nebula, where stars and planets begin their long journey into existence. The vacuum is pregnant with potential. There are planets out there stranger than anything we've dreamed of. Take HD 1T9733b, a gas giant where it rains glass sideways in 5,000 mile-per-hour winds, or 55 Cancri e, a planet likely made of diamond, its carbon-rich structure compressed by immense pressure, or Gliese 581c, a world that may lie just within its star's habitable zone, with the potential for liquid water. Some planets orbit two suns, like scenes from a sci-fi movie. Others are scorched, tidally locked hellscapes, where one side is a molten desert and the other an endless frozen night. Our universe is expanding, not just objects moving through space, but space itself stretching. Galaxies aren't traveling through a void like ships through an ocean. The ocean is growing beneath them. This discovery, first observed in the redshift of distant galaxies, means that the universe once had a beginning, a single moment of rapid expansion, the Big Bang. And that expansion continues today, accelerating due to a force we still don't fully understand. Dark energy, a mysterious pressure pushing everything apart. Then there's dark matter. We cannot see it. We cannot touch it. But it's there. Its gravity holds galaxies together, keeps clusters from flying apart. It makes up over a quarter of the universe, yet we don't know what it's made of. It neither emits nor absorbs light. It passes through us every second. Like a ghost overlaying reality, shaping the structure of everything we see. Time, too, is not as it seems. In the early universe, the rules were different. Moments after the Big Bang, time and space were chaotic, energy and matter in a soup of particles and raw forces. The four fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were once one, unified. Since then, they've separated, cooled, and structured the cosmos. But deep inside particle accelerators, we try to reverse that clock, to glimpse the unity, the primal heartbeat of the cosmos. And yet, with all this knowledge, mystery reigns. We've mapped only a small fraction of the stars. We've only just begun to catalogue exoplanets. We've never been farther than the moon. The observable universe is vast. But beyond it, we don't know. There may be more, far more. Infinite realms, parallel universes, entire other realities with different laws of physics, born from the same cosmic fire as ours. And in all of it, here we are. A species that can ponder the beginning of time, that can send robots to Mars and probes beyond the edge of the solar system, that can build telescopes so precise they can see light from galaxies 13 billion years old, light that left when the universe was still in its infancy. We are the universe, becoming aware of itself. Somewhere far from any star, in the deep interstellar dark, a spacecraft drifts in silence. It's called Voyager 1. Launched in 1977, now over 14 billion miles from Earth. It carries with it a golden record, a time capsule of humanity, music, greetings in dozens of languages, sounds of life on Earth, a whisper to the stars. Voyager 1 has left the solar system. It is now in interstellar space, the first object made by humans to ever do so. It continues its journey, untouched, undisturbed, on a trajectory that may outlast our species. For billions of years, it will drift in the quiet, a ghost of Earth sailing through the endless night. On Earth, the sky looks still, but look closer, and you'll find it's alive with motion. The stars are moving. The constellations we know are temporary, fleeting sculptures shaped by our position in time. In 50,000 years, Orion will look completely different. In 1,000,000 years, today's night sky will be unrecognizable. The stars we navigate by are travelers themselves, orbiting the galactic center, pulling against gravity, drifting through a galaxy that spins like a pinwheel of fire. The Milky Way, our home galaxy, is vast, over 100,000 light-years across. But it isn't alone. We're on a collision course with the Andromeda Galaxy, a spiral galaxy twice our size. In about 4 billion years, the two will merge, tearing and reshaping each other in a gravitational ballet. Stars won't crash. Space is too empty, but their orbits will change. New stars will be born. the night sky will erupt with arcs of starlight, and eventually a new galaxy will form, elliptical, larger, older, a silent monument to cosmic rebirth. Not all galaxies are peaceful swirls. Some are active, chaotic, burning from the inside. At their hearts are supermassive black holes devouring matter so violently that jets of energy blast out across millions of light years. These are quasars, the brightest objects in the universe. They shine with the light of 1 trillion suns. Yet they're powered by darkness, by gravity crushing light itself. When we see a quasar, we are looking back in time to the young universe when galaxies were still growing, still colliding, still becoming. The universe is not cold because it lacks energy. It is cold because it is old. As it expands, the energy of the Big Bang spreads thinner. Today, space itself holds a background temperature of just 2.7 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation. It fills all of space, a faint radio hum from the beginning of time. When you see static on an old television screen, a tiny fraction of that fuzz is the leftover light from the birth of the universe. Gravity is not just a force. It's the bending of space and time. Massive objects, planets, stars, black holes, distort the fabric of reality around them. Einstein showed us that light can curve, that time can slow, that space is not a stage, but a participant. And this bending of reality isn't just theory. We've seen it. When a massive galaxy sits between us and something farther away, it can act like a lens, bending and magnifying the distant light. We call this gravitational lensing. It lets us see galaxies so far away they'd otherwise be invisible. It's as if the universe is helping us see itself. And yet, for all our knowledge, we've only just begun to grasp the full picture. The vast majority of the cosmos is made of things we can't see or explain. Ordinary matter, everything we've ever touched or measured, makes up less than 5% of the universe. The rest is dark matter and dark energy. Invisible. Mysterious. We don't know what it is. We don't know where it came from. But it controls the structure and fate of everything. It's the shadow behind the stars, the silence beneath the light. Every now and then, Earth is reminded of its fragility. An asteroid streaks across the sky, burning bright as it tears through the atmosphere. Most disintegrate harmlessly. Some leave craters, scars from impacts long past. 65 million years ago, such an impact changed everything. It ended the age of dinosaurs. It cleared the way for mammals. For us. We are here because a rock fell from the sky at the right, or wrong, time. And there are still many more out there, orbiting quietly, watching, waiting. But space isn't just death and distance, it's potential. On moons like Europa and Enceladus, icy shells hide oceans below, heated by tidal forces. These alien seas may be teeming with microbial life. We've seen plumes of water erupt into space, carrying hints of organic molecules. If life can thrive there, in darkness, under pressure, without sunlight, then maybe life is everywhere. Maybe biology is not a miracle, but a pattern, a thread that runs through the fabric of the cosmos. Even on Mars, the red planet, there are hints. Ancient riverbeds, polar ice caps, traces of methane in the air, a past that may have once been warm, wet, and alive. Robotic explorers crawl its surface now, drilling, analyzing, searching, not just for curiosity, but for connection, to know whether Earth is unique or simply one chapter in a much larger story. Black holes are often seen as the end, the final stage of stellar collapse, a place where even light cannot escape. But in truth, they may be something more, something stranger. At their heart lies a singularity, a point of infinite density where the laws of physics as we know them break down. Space and time themselves curve inward toward this point, like water spiraling down a drain. But some theories suggest what lies beyond isn't a void, but a bridge, a wormhole, a doorway to another place, or another universe. These ideas remain speculative, but tantalizing. In the universe's deepest pits, we may find not destruction, but connection. And yet, black holes don't just consume, they shape galaxies. The one at the center of the Milky Way, silent and immense, may regulate the birth of stars through its gravitational pull. In a strange irony, the very things that destroy light may also give structure to the galaxies that cradle it. They are not simply cosmic monsters, they are architects of the cosmos. As we observe the universe, we are not just looking out into space, we are looking back in time. Because light has a finite speed, every star we see is a snapshot from the past. The moon is 1.3 seconds away, the sun 8 minutes, the nearest star over 4 years. The Andromeda galaxy, 2.5 million years. When we gaze into the night sky, we are reading ancient messages, light that has traveled across unimaginable distances to meet our eyes. A galaxy seen at 13 billion light years away is a glimpse of the infant universe, when the first stars were just beginning to shine. And those first stars were unlike anything we know. They were giants, massive, short-lived, and made only of hydrogen and helium. Born in a time before carbon, oxygen, or iron, these primordial stars burned hot and died fast, seeding the cosmos with the first heavy elements. From their ashes, later generations of stars emerged, and with them, planets, moons, and eventually, us. Every atom in your body was once inside a star. You are not just in the universe, you are of it. We dream of faster-than-light travel, of starships, warp drives, wormholes. And while current physics forbids it, some concepts push the boundaries. The Alcubierre drive, a theoretical model, proposes bending space around a ship, compressing space in front and expanding it behind. The ship itself never moves faster than light, but the space around it does. It's speculative, unproven, and would require negative energy, something we've never seen. But it represents the essence of exploration, the desire to go beyond what's known, to chase the horizon. And there is no horizon more daunting than time. What happens to the universe in the far future? The galaxies will continue to drift apart. Star formation will slow. The stars will age, dim, and die. White dwarfs will cool. Black holes will evaporate through Hawking radiation. Over trillions, then quadrillions, then quintillions of years, everything we know will fade. Matter itself may decay. What remains is the heat death, a state of maximum entropy where no energy flows, no stars shine, and the universe becomes cold, dark, and still. But perhaps that is not the end. Some physicists believe that even then, new universes may emerge, that black holes could give birth to new Big Bangs, that our universe is just one in a cycle of births and deaths, a pulse of cosmic breath on a scale beyond comprehension. Or maybe we are a quantum accident, a fluctuation in a greater multiverse, a bubble of order in an ocean of chaos. And still, we look up. With telescopes on mountaintops and satellites in orbit, we scan the heavens. We listen for radio signals. We model alien climates. We ask questions no other known species has ever asked. We are curiosity incarnate, a flicker of awareness in a sea of stars. We build machines like the James Webb Space Telescope to see the first galaxies. We design rovers to crawl across alien dust. We train AI to analyze starlight, hoping to detect the breath of life on distant worlds. Because maybe we are not alone. Across the void, in the spaces between stars, we've been asking a question older than our species. Are we alone? For over half a century, we've been listening, Giant radio dishes point toward the stars, scanning for artificial signals, patterns, pulses, mathematical structures that nature doesn't make. We've heard only silence, but the silence is not proof of solitude. It may simply be the distance between civilizations, or the briefness of their existence, or the strangeness of their language. A message could be streaming through us right now, encoded in a frequency we don't yet understand. Life, as we know it, requires liquid water, organic molecules, energy. But we found these ingredients in surprising places. Beneath the ice of Jupiter's moon Europa, in the methane lakes of Saturn's Titan, in ancient Martian riverbeds. If life can arise in one place, it may arise in many, and it may not resemble us at all. On Earth, life has adapted to boiling vents, freezing poles, crushing pressure, and acidic swamps. Life is resilient, adaptable, creative. Perhaps the universe is too. Some scientists believe microbial life could exist now, hidden in alien oceans or clinging to the clouds of Venus. Others look to distant exoplanets, thousands of them, orbiting distant suns. We've found rocky worlds in habitable zones, some with atmospheres, some with strange chemistry. We've even started to detect biosignatures, hints of gases that, on Earth, would suggest life. Nothing confirmed, but enough to keep asking, enough to keep hoping. And then there is the Fermi paradox. If the universe is so vast, so old, so full of planets, where is everyone? One answer may be distance, another, time. Civilizations may rise and fall like sparks in the dark, too brief to overlap. Or maybe the intelligent ones don't broadcast. Maybe they watch in silence, or hide, or evolve into something we wouldn't recognize. Perhaps consciousness itself is rare, or fleeting, or self-limiting. But what if they're out there, old, wise, ancient beyond imagination? Would we even recognize their presence? Would their technology bend space, harness stars, manipulate matter at the quantum level? Would they build Dyson spheres, vast structures around stars to capture energy? Would they live in simulations, abandoning physical form? Or would they be simple, biological, curious, like us, searching the stars for signs of company? In 1974, we sent the Arecibo message. A radio signal beamed into space toward a globular cluster 25,000 light-years away. It contained information about our species, our DNA, our solar system. It was symbolic, more art than outreach. But it marked something profound. The moment we said hello, knowing we might never hear back, knowing the odds. We sent the message anyway. If we ever do make contact, what then? Will we understand each other? Will it be a moment of awe or fear? Will we see in them a mirror of our potential or a warning of our limits? The first alien signal will be the most important discovery in human history, not because it tells us who they are, but because it confirms we are not the only question the universe has asked. And if we never hear from anyone else, then that means something too. It means intelligence is rare. It means life is precious. It means, for now, we are the only known voice in the cosmic dark. And that voice matters more than we thought. Because whether or not we find others, we have already found each other. And we have the tools, the mind, the vision to keep reaching. The stars have always called to us. For most of human history, they were myth and mystery, painted on the night sky like stories we could never touch. But now, for the first time, we stand at the threshold. The tools we build are no longer just for looking up. They are for leaving. Rockets break the grip of Earth's gravity. Rovers crawl across distant worlds. Space stations orbit above us. Fragile outposts of life in a place where no life belongs. We are learning, slowly, cautiously, but inevitably. Still, the stars are far. The closest one, Proxima Centauri is over 4 light-years away. With current technology, it would take tens of thousands of years to get there. But we are dreamers, and we are builders. Projects like Breakthrough Starshot imagine tiny light sails pushed by lasers, miniature ships traveling at 20% the speed of light. Others dream of fusion drives, antimatter propulsion, or even warp bubbles, theoretical ways to cheat distance by folding space itself. These are not science fiction fantasies. They are ideas in development, blueprints waiting for breakthroughs. To live among the stars, we must change, not just our machines, but ourselves. On long interstellar journeys, generations may live and die aboard ships. Some speak of cryogenic sleep, others of digital consciousness, uploading the mind into data, sending ourselves as information rather than flesh. And if we reach distant planets, we may not remain human as we are now. We may become something new, adapted, engineered, interwoven with AI, shaped by alien gravity, alien air, alien light. But before we go far, we must go nearby. The moon is our testing ground, close enough to reach, harsh enough to teach. We will build there, habitats shielded beneath regolith, solar farms capturing endless sunlight, laboratories studying how life copes with barren rock. And then Mars, a world with winds and seasons and canyons deeper than any on Earth. We'll send crews, then settlers, then children born under a pink sky. They will not remember Earth the way we do. To them, it will be the myth. Terraforming may come next. Vast projects to warm planets, thicken atmospheres, release water. It could take centuries, millennia. But we've changed Earth accidentally in a few short generations. Given time and will, we could sculpt other worlds deliberately. Mars, Titan, even the moons of Jupiter could one day be wrapped in domes, crisscrossed with greenhouses, seeded with life. Not just to escape Earth, but to spread it, to become a life-bearing force in the galaxy. And what of Earth itself? We must protect it, not only because it is our home, but because it is rare. So far, we have found no other place like it. If we ruin it, we may not get another. If we save it, it can remain our root, our memory, our origin story. A pale blue dot that birthed a species capable of dreaming far beyond its sky. As we grow, we may form a civilization that spans planets, moons, eventually stars. A Type 1 civilization, mastering the energy of a world. A Type 2, harnessing the full power of a star. A Type 3, commanding the energy of an entire galaxy. These are not tomorrow's goals, but they are not fantasy either. If we survive, if we cooperate, innovate, and endure, the stars are not the limit. They are the beginning. Artificial intelligence may be our partner in this, or our successor. Machines that think faster than us, build smarter than us, learn beyond us. They may one day run starships, build cities on Europa, mine asteroids, terraform planets. They may teach us things we cannot imagine, or carry our legacy if we fall. And if intelligence evolves in the galaxy more than once, it may not always be biological. The future of thought may be silicon or quantum, or something we do not yet have words for. We are at the very start of this journey. A species only 300,000 years old. A civilization barely 6,000. A spacefaring race just 60. We are children with fire, building towers to reach the sky, asking ancient questions with new tools. We will make mistakes. We will fall. But if we rise again, and again, the universe will open. And what waits out there? New physics, new life, new challenges, new beauty. Maybe we will meet others. Maybe we will outlast the stars. Maybe we will become the stars, burning with knowledge, scattered across the galaxy, eternal in light, if not in form. Because the true story of space is not distance. It is not silence. It is potential. and the greatest chapter may still lie ahead, written not in stardust, but in the minds of those who dare to reach beyond everything they've ever known. Eventually, the stars will go dark. One by one, their fuel will run out. The great engines of the cosmos, forged from gravity and hydrogen, will sputter and die. Red dwarfs will linger, glowing dimly for trillions of years, the last to fade. But even they will succumb. In the far future, the universe will enter its degenerate era, an age of ash and ember, where white dwarfs, neutron stars, and black holes are all that remain. No new stars will be born. No new light will emerge. The galaxies will be cold, quiet ruins drifting in a void grown unimaginably vast. Black holes will dominate. They will continue to consume, to merge, to grow. And then, even they will begin to vanish. Slowly evaporating through Hawking radiation, they will release their mass as a trickle of particles into the dark. The largest will take a Google years to fade, a number with 100 zeros. And when the last one disappears, there will be nothing left that shines. No matter, no motion, no heat. Only particles spread so thin they may never touch again. This is the heat death, not fire, but stillness. Entropy maximized. A universe where everything has happened and nothing remains to happen. No gradients, no energy to harness, no change. It is a state not of destruction, but of final equilibrium. It is the end of all stories told in matter and time. And yet, some theorize this may not be the final end, that quantum fluctuations may create new universes, bubbles of order in the sea of stillness. Some may grow, inflate, ignite into new spacetimes with their own physical laws. Perhaps ours was born this way. Perhaps the multiverse is real, an endless fractal of beginnings, each unaware of the others, each infinite in its own right. Some suggest our universe may be a simulation, not a metaphor, but literal code, running on a substrate we cannot perceive. That everything we know, stars, planets, consciousness, is emergent behavior within a deeper reality. The simulation hypothesis posits that advanced civilizations could create entire worlds indistinguishable from base reality. And if they could, they likely would. And if they would, we may be inside one now. But even if that is true, it changes nothing. The stars still burn, the void still stretches, the questions still matter. Whether written in carbon or code, we are here, experiencing, wondering, becoming. Consciousness, the strangest force in the universe, may be its most powerful. It can't be weighed, it can't be seen, yet it shapes civilizations, tells stories, asks questions, feels awe. From the structure of neurons to the fabric of space-time, we are finding connections. The brain and the cosmos, both networks, both pulsing with information. Some believe consciousness is fundamental, woven into the universe like space and time. Others see it as an emergent property. The brain, a temporary mirror held up to the infinite. And still the mirror reflects. Still we wonder. Still we reach. No other creature we know of has ever looked up and asked why. No other planet, as far as we can tell, has grown eyes to see the stars. That may change, or it may not. But for now, in this moment, we are here. A flicker of thought on a grain of dust, orbiting a small star in a quiet corner of a vast and ancient galaxy. And that, against all odds, may be enough. In the deep architecture of the cosmos, patterns repeat. Spiral galaxies mirror the whirlpools in our oceans. The filaments of the cosmic web resemble the neural pathways of the brain. The golden ratio appears in the arms of galaxies, in the growth of seashells, in the branching of trees. The universe, in its vastness, echoes itself, from the micro to the macro, from the subatomic to the galactic. These patterns are not proof of design, but signs of underlying order. Structure in chaos, law in the unknown. The universe is not uniform. It is lumpy, uneven. Galaxies clump together in webs, connected by filaments of dark matter, separated by vast voids where almost nothing exists. These cosmic voids are hundreds of millions of light years across, expanses so empty that a single galaxy passing through would be like a grain of sand in the Pacific Ocean. And yet, even here, gravity whispers. Even here, expansion continues. Quantum mechanics tells us the universe is not made of things, but of probabilities. Particles blink in and out of existence. Locations are uncertain until measured. Entanglement links particles across space, instantaneously, as if the universe itself does not care about distance. Reality, at its core, is fuzzy. The closer we look, the less solid it becomes. And yet, out of that uncertainty emerges everything: matter, energy, time, thought. There are particles that can pass through entire planets without slowing down. Neutrinos, ghost particles, are created in nuclear reactions, in the hearts of stars, in supernovae. Trillions pass through your body every second, unnoticed. They are messengers from the core of suns, from the edge of the universe, from moments after the Big Bang. They are the silent threads connecting us to everything. There are places where time moves differently. Near black holes, seconds stretch into hours. In accelerating frames, clocks run slower. This is not illusion. It is the shape of reality. A traveler moving near the speed of light could journey across the galaxy and return to find centuries passed at home. Time is not fixed. It bends, warps, flows. It is part of space, and space is not a backdrop. It is alive, shifting, reactive. The universe is not a stage, but a player, and perhaps the strangest truth of all. The universe has no center, no edge, no outside. It is not expanding into anything. Space itself is expanding, everywhere, all at once. Every galaxy sees every other galaxy moving away. The fabric is stretching, the scale is growing, and yet, from inside it feels still. Motion without movement, infinity without direction. The laws of physics are not merely descriptions. They are constraints, but also keys. They allow life to emerge, stars to burn, atoms to bond, minds to think. And they are, as far as we know, the same everywhere. The same on Earth as in galaxies 10 billion light-years away. This uniformity suggests a common origin, a singular birth, a moment when all things began, hot, dense, bright, and then expanded, cooled, evolved. And yet, even now, the universe is not done becoming. Stars are still born, galaxies still collide, planets still form. Somewhere, right now, a world is cooling from fire into stone. Somewhere, right now, life may be waking up for the first time, crawling from the sea, gazing at its own sun, wondering. Somewhere, right now, a civilization may be transmitting its first signal. Somewhere, right now, we may be the signal they're hearing. Because this is not just a story of stars. It is a story of time, of emergence, of consciousness finding itself in the mirror of space. The universe does not explain us. We explain the universe, and in doing so, we give it meaning. The universe is not static. It is not a finished canvas, but a work still in progress. A slow, unfolding act of creation, playing out on a timescale so vast we can only catch fragments. In every supernova, in every merging galaxy, in every newborn star, the story continues. It is a cosmos in motion, not drifting aimlessly, but evolving, shaped by laws we barely understand, into forms we can barely imagine. Between the atoms in your hand is empty space, vast and silent, proportionally as empty as the distances between stars. The solidity of matter is an illusion of quantum fields and electromagnetic forces. You are not made of things, but of relationships, interactions, fields vibrating into what we call matter. And yet, from this emptiness emerges thought, memory, love, a mind aware of itself, looking outward and inward all at once. Your body is made of hydrogen from the Big Bang, carbon from dying stars, calcium from ancient supernovae. You are the dust of collapsed suns, organized by DNA into a form that can ponder its own origins. Life is the universe folding in on itself, a pattern of molecules complex enough to ask why. This is not philosophy, this is physics. Every breath you take is shared with the past. The oxygen in your lungs may have passed through the leaves of trees that grew before you were born. The water in your veins may have once flowed through ancient rivers, ancient animals, ancient storms. You are not separate from the earth, and earth is not separate from the cosmos. It is a vessel, a temporary concentration of matter and energy, forged by a billion accidents and a few consistent laws. And still, there is so much we do not know. We do not know what dark matter is. We do not know why there is more matter than antimatter. We do not know how consciousness arises from tissue, or if it even does. We do not know if the constants of nature are truly constant. We do not know if time had a beginning, or if it loops, echoes, branches into infinite paths. We do not know how the universe will end, but we know that everything that begins also changes, that all structures, all stars, all thoughts are temporary, that impermanence is not failure, but nature. The arrow of time moves in one direction, driven by entropy, the tendency of systems to move from order to disorder. And yet within that law, pockets of complexity emerge. Galaxies, solar systems, life. This is the paradox. The same universe that trends toward simplicity also gives rise to stars, cells, minds. The same randomness that scatters also creates. It is within this tension, between chaos and order, that life finds its window. It is here that meaning is born, not from design, but from participation, from existence itself. You are not separate from the cosmos. You are a way for it to feel, to ask, to wonder. A brief arrangement of particles tuned by time into awareness. And as you look out at the stars look back through you, because for a moment, in this tiny corner of space, the universe knows that it is vast, and it knows that it is beautiful. There is a silence in space that is absolute. It is not quietness as we know it, but the absence of medium, the absence of air. Sound cannot travel there, and yet the cosmos speaks. It speaks in light, in radiation, in gravity. The collision of neutron stars sends ripples through space-time, gravitational waves that stretch and squeeze reality itself. We have built instruments so sensitive they can detect these ripples from galaxies millions of light years away. With them, we listen not with ears, but with mathematics. We hear the universe through distortion. And in that distortion, we find new truths. Space is not smooth. It is not flat. It curves around mass. It twists near spin. It dances under tension. It expands. It vibrates. It bends. It is not the stage upon which the universe acts. It is part of the cast. It interacts. It flexes. It remembers. Black holes may be the ultimate memory, not just devourers, but recorders. According to quantum theory, information cannot be destroyed, and yet black holes seem to swallow it forever. This contradiction between relativity and quantum mechanics is one of the greatest puzzles in physics. Some believe that information is encoded on the event horizon, like a hologram. Others believe it leaks out in Hawking radiation, twisted beyond recognition. Others still think our understanding is too limited, that something deeper awaits discovery, a new theory uniting gravity and quantum mechanics at last. That theory may not just explain the universe, it may explain everything, why there is something rather than nothing, why the laws of physics take the form they do, why the cosmos permits life, thought, love. We call it the theory of everything, and we have not found it yet. But every equation, every telescope, every experiment brings us one step closer to unveiling the machinery beneath the veil. In all directions, the universe looks the same. No matter where we point our instruments, we see galaxies drifting away, redshifted by expansion. This symmetry suggests something astonishing. There is no preferred place, no center, no edge. Every point in space sees the same outward motion. We are not in a special location. We are not above or below. We are not central. We are simply within, embedded, carried by the flow. And yet, for all its indifference, the universe has given rise to meaning. Not absolute, not universal, but emergent. Meaning is not written into the stars, it is written into minds. It is what arises when consciousness collides with time. We invent it. We suffer for it. We live by it. And in doing so, we become something greater than matter. We become participants in the unfolding of a reality that did not ask for us, but allowed us anyway. The universe does not owe us comfort. It offers no guarantees, no protection, no permanence. But it permits us. It permits stars to form. It permits chemistry to dance. It permits biology to emerge. It permits atoms to arrange themselves into minds that can imagine futures, remember pasts, and build tools to reach beyond what is visible. That permission, that fragile, narrow band of possibility, is everything. And though we are small, we are not powerless. Though we are brief, we are not irrelevant. We are perhaps the only voice the universe has ever had. A single point of awareness in a sea of silence. But a point that burns, that questions, that dreams. A point that, even knowing its own impermanence, still dares to reach for the stars. In the beginning, there was silence. A silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies, each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age, about 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light years in radius, beyond which the universe fades into an unknowable darkness. And yes, that horizon's radius is larger than 13.8 billion light years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us. A view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball, there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling. An infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve, like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities, unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see and all that we cannot see was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others. Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water, each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow, and if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions, it fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe. And inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know. A sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist. And perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe, mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the Standard Model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water, yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all, it's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected. Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought. What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell space-time how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well, a constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist, and why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teems with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field filling space, one that can vary from place to place or era to era,
and whose properties we have yet to determine. Another wild possibility: perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy.
For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up, and we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity, wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trapdoor. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, the tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time, you reach the central singularity and are crushed. Your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of space-time, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon. We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding — we predicted them, then observed them — and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately,
Yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past. We anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics, ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states? Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars,
but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons one by one through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality. The many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others. So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected.
For example, two photons can be entangled in polarization such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus, their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory, confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer, it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme, perhaps in the subsurface oceans of icy moons like Europa, or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size, and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, but it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, and soon next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion. that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble. 100 light years in radius, and we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine, will find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale. Inert matter becoming sentient. Yet it happened. In us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states, for instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as phi, Fef. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences. For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole, or with fundamental fields. These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us, because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions. Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism,
the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, but that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed, though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces, the Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10^35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth, to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments, extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery and we respond with curiosity, a fundamentally human trait, perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes, telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory, a momentous achievement that could answer some of those questions.
maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality. Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection. You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink, and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter. Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing, and then finding even more not knowing, is likely endless. And that is good. It means our descendants, be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, we'll go there, and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer: the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. The spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable.
Yet none of those physical things inherently produce meaning. A star doesn't seek meaning. A galaxy doesn't appreciate beauty. But we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound. But there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, "There is more, so much more." It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle. But that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the Earth, perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game,
And perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the earth, a reminder that even the local theatre of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping space-time itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human. The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime. In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds, suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, why, how, what's beyond, or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life. That is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious, and it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive.